isotropic and spatially homogeneous. There's a whole family of rotationally symmetric models which have been investigated in great detail because they're very easy to investigate. And there are the Bianchi models, which are the ones I've spent a great deal of time on because they are complicated, but they can be handled still. And that's what that dynamical system book looks at. For the inhomogeneous models, I've lumped, these are the two-dimensional ones with a two-dimensional surface of homogeneity. These include, there aren't any here, they can't exist. These are the Bondi-Tolman family, and these are enormously helpful in examining inhomogeneities in cosmology. These are exact solutions with spherical symmetry, but the spherical symmetry, they can depend on space and on time. And a huge amount of work has gone into those models to study things like gravitational lensing, like cluster formation, and so on. And then there's a family of generic models here in which there's no isotropy group and they are inhomogeneous. And we actually know quite a lot about such models, but they're difficult to use because they have such low symmetry. And then there's the ones where there's just a one-dimensional group, and then there's the ones with no symmetries. And curiously, we have got three sets of families of exact solutions of models with no symmetries whatever, exact solutions of the Einstein equations. It's really quite an amazing achievement that we've got those. But then the real point I want to make is that the real universe is here. Okay, the real universe has no symmetries. And whenever we use any of these other models, including the Robertson-Walker, to model that, we must remember that this is an approximation, and the real thing is not in any of these categories. The real thing lives down there in the space where there's no isotropy and there's no spatial homogeneity. Okay, that's what I wanted to do now. This afternoon I'll be talking about the standard, the concordance model and its coherence, and tomorrow, just for fun, I'll be talking about local physics in the expanding universe. Yes.
I agree with you strongly that things like multiverse and anthropic principle do not belong in science. So I applaud you for saying that. So let me ask you a question. Do you think the anthropic principle is falsifiable?
Is the anthropic principle falsifiable? No.
It's not falsifiable.
It has to be used as a selection criteria.
Well, let me ask you this.
Well, when you say the anthropic principle, it's like saying is Mach's principle falsifiable? There's so many formulations, we have to discuss which particular formulation we're talking.
Okay, and let's say a moderately reasonable formulation of the problem. And now I'll try something out on you. I gave a talk at a neutrino conference earlier last year in Australia. And my talk consisted of the following. The present data on the neutrino mixing matrix looks very much like it's a very special matrix with entries like 1 over square root 2 and 1 over square root 3, things like this. Now, of course, that can never be decided experimentally, because experimentally it will always be just some number with some error.
Right.
Now, the question I have is that if, and as far as I know, and as far as anybody knows, I think nobody would claim, even the strongest anthropic principle of inhabitants would not claim that neutrino mixing has anything to do with human existence. Now, if the theorists in this field, neutrino theorists, work very, very hard and manage to derive this special matrix,
Yes.
would the anthropic principle be falsified? Or they just say, because
it's got nothing to do with it.
Right, and because in different universes, presumably, those people would say it's just a random accident. But then they could always say, well, no, there's some deeper principle that would give this, and so on, comes out of, the nth successor of string theory, or whatever.
All right.
Is it falsifiable if neutrino physicists go to work hard?
Well, the first point I would make is you must be just a little careful assuming that this neutrino mixing does not have to do with the existence of life, because it might have to do, for instance, with the amount of radiation given off by the sun or by supernovae. And it's not impossible I would find a link through there to the existence of life. No, all you're saying is, I don't think it would disprove it. I think it would simply say it doesn't, the anthropic principle shrinks the possibility space, but it doesn't shrink it to one point. It just shrinks it to an open domain, and I think that's absolutely fine. So I don't think you would disprove it that way. The most important use which has been made of it in a practical sense is Weinberg's use, which he's trying to justify the present value of the cosmological constant. Now, that is really extraordinary because he's kind of admitting that sort of a distribution of cosmological constants would be huge, and then there'll be this tail, and in effect, he's using the anthropic principle to say we're way out in the tail over there in the real universe.
Well, that's Vilenkin's criticism, that everything depends on the finite distribution.
Yes. Yes.
But on the other hand, I find Weinberg's use actually acceptable to me because it's relatively mild, right? It's using an experimental fact, which is, in physics we use experimental facts all the time. He's using one experimental fact, namely that galaxies exist.
Yeah.
Why not? What is your objection to that?
I don't object to that at all. The problem is that he explicitly states that there is an ensemble of universes, and he talks about the various ways it could happen. It could be multiverses in the quantum kind of way, or it could be chaotic inflation, or it could be disjoint. So it's very, very vague at that point. And then the point simply is that there isn't any evidence that any of these other universes exist. So sure, you explain, it's a device to explain what is in fact incredibly improbable by manufacturing in your mind this ensemble of universes. Now, manufacturing in your mind is one thing, but to claim that they actually exist out there is a totally different point.
Well, let me give you another example. 300 years ago, I could have used the anthropic principle to prove that the Earth must be flat. Because if it isn't, we will fall off. And we wouldn't exist. Now, do you accept that as an argument against anthropic?
The anthropic principle will always be phrased within your knowledge of physics of the time, and within your knowledge of physics at that time, that would have been an acceptable use. What has changed is the interpretive framework within which you're applying it, and that will also happen to us.
Okay, well, it's very hard for me to argue with you because we're on the same side.
But let me use this opportunity just to say one other thing, which I really... with my friend Bill Sturger, we've put an article on, and Uli Kirchner, who is here, we put an article on multiverses on the web, in which we make the following point. Many of the people who talk about multiverses talk about infinities of universes. Now, I have a real problem with the idea of infinity of universes, and we give a lovely quote from David Hilbert, who says, infinities is a nice mathematical idea, but it is never realized in physical practice. And I think that's a really interesting thing to talk about. It relates to what you were saying earlier. Yes, it relates to the cutoff, precisely. Because, in fact, the mathematical continuum which underlies theoretical physics, I think, is not a real thing in physics, and that's what you're saying. In fact, that there's a quantization which cuts off that. And I think you might find this quote by David Hilbert really nice, because he really says that infinity is a nice conceptual idea, but it never occurs in the real universe. And it gives the cutoff in exactly what you were saying. So we're agreeing in that. But there's a real problem with the claim that there's this infinite number of universes, because infinite is infinite. It's not a large number. If you take seriously the idea of all that can exist exists, which is the phrase that they use. Okay, so now think of a Robertson-Walker model with a given density parameter, and then you've got to take all values of the Hubble constant for that density parameter of everything. That is an uncountable infinity of universes out there. It's uncountable. It's mind-boggling that people can think this actually exists. And there's a very, very nice little book by Martin Gardner recently come out called On the Multiplicity of Universes and Blackberries, or some title like that. And at the end, he has a very caustic comment on the scientists who are out there suggesting there is an infinite number of other universes. He closes it off by saying there is no more evidence that there are two universes. There's no evidence even that there are two universes, let alone an infinite multiplicity of them.